Hello, everybody. Good morning.
Good morning, Professor.
I just want to share my screen. So last time we agreed that we will revise this part. Here. Yes. I mean, last time we agreed that we need to revise this gradient descent part and add this momentum term. So it's just very quickly, we need to go through it quickly. I mean, we need to define a cost function. And this cost function, it should be differentiable and it should be convex to be sure that we will be able to reach this bottom point here, and to be guaranteed that we will be able to minimize this function. So we need to, so for example, if we have a cost function like square error, like for example, I mean, we calculate error, for example, it would be nice if we can square this error. So the error function will be convex. So we will be sure that we will be able to minimize this error. So, and last time we used this example. This is an example of convex function and the non-convex function. And the problem of non-convex function is that we have some local minima here. So there is no guarantee that we will not hit this point and we will not stay here. And to avoid this, maybe you need to run your algorithm several times and try to calculate the error each time, for example. So you can see that you have two types of errors. For example, you have this bottom point and this point here. This is very simple example. We have this function 5x squared plus 2x minus 4. We need to find the gradient, and the gradient, it's the first derivative of this function, which will be 10x plus 2. 2 times 5, it's 10x plus 2x, it will be 2. And after that, the rule for updating x, it will be x equal x plus delta x, for example. And the delta x will be minus eta minus learning rate multiplied by the gradient. So delta x here, this is a rule for updating x, but delta x equal minus eta. If we need to minimize, it should be minus learning rate multiplied by the gradient, which is delta x here. So we will repeat this process several times until we are able to minimize the function. So I try to find another function which is non-stochastic, because there is no guarantee that your cost function will be non-stochastic. And this non-stochastic, I mean, it does not necessarily go towards optimum. You will optimize, you will minimize your function, but there is no guarantee that you will be able to reach this global minimum, for example, because if you are starting in this point here, at that point, you will go to this local minima, not global minimum. So this is a problem. So the update rule here, it's similar to this for the convex function. It will be omega equal omega, or omega t plus 1 equal omega t minus eta minus learning rate multiplied by the gradient. So it's the same as we did before. The problem, and I mean, reality is much more complex than those simple functions. So usually you will have a cost function which is really very complex. It has very difficult and very complex terrain, for example. So minimizing this function is really very complex, and it's difficult to find the mathematical expression for this cost function, for example, to solve it analytically, for example. So we have to solve it numerically using gradient descent. This is the example which we did last time, and as you can see here, we have this function. We defined a function here. So the function called 5x squared plus 2x minus 4. We will find the first derivative of this function, which is 10x plus 2. We will run this gradient descent for number of epochs using some learning rate, for example, eta equal 0.01, for example. We will run it for number of times, and we will run it until the gradient, for example, is less than or equal 0.01, for example. I mean, usually you will start at some location here by random, and you will stop at the bottom here when the gradient equals 0, in fact, because at the bottom here the gradient equals 0, the slope of the line equals 0, which means the slope is parallel to the x-axis. So we will do this process until the gradient is close to 0. Now we need to add this momentum term, because last time we said that if the function is non-convex, it will be a problem, and we need to add another term which can help us to cross this local minima, for example. So we have this momentum, or SGD, stochastic gradient descent with momentum, is a method which helps us to accelerate the gradient, gradient vectors in the right direction. We just need to accelerate, because maybe the gradient itself is not enough. So in this case, we need to accelerate the gradient in the right direction, which might lead to faster converge. So, and the updating rule here, it will be the same: omega k plus 1 equal omega k, or you can just say omega plus equal delta omega k, for example. And the delta omega k, rate of change of omega, it will be minus learning rate minus eta multiplied by the gradient plus the momentum term. This momentum term, its factor multiplied by the last gradient, last rate of change. So we have delta omega k here. We need to keep or save the old value, delta omega k minus 1, and we need to multiply this one by a factor. It could be 0.2, 0.5, 0.6. So it's a hyperparameter also, which we need to select. So in this case, the updating rule. In the updating rule, we will have two variables which we need to select. We have the learning rate, we have the momentum term, which we need to define. So I try to simulate it for you. So we need to minimize a non-convex function, and we need to select a convex function which has those nice bumps, for example. So we have some local minima here, another local minima in that place. Maybe I will use my pen here. So we have here, I just need to annotate why it's not working. Oh, sorry for yes. So for example, I need to go to the function one more time. I don't know, is it forward or backwards? Yes. So I don't know. I just check my just 1 second, please. I try to fix something. I try to write on my computer here, but for some reason it's not working.
I don't know. It seems like your sketching function is active.
Yeah.
Yes,
there is. Maybe I need to share my screen one more time. Now you can see my screen, right?
Yeah.
Okay. Because I try to sketch, but it's not working for unknown reason. Annotate. Yeah, it's not working. I don't know. So anyway, we have this learning rate and the momentum term. Sorry if I cannot use my no, it's not working for unknown reason. It's a strange area. So we can just there's something strange. Okay, so we can just go forward. So we have this function, and this function, as you can see, it has some local minimums and a global minimum, and we need to plot this function, and we need to use stochastic gradient descent to find x, which will minimize this function. So this function, it's function of x. So if of x equal x multiplied by x minus 1, multiplied by x minus 2, x minus 3, x minus 4 times x plus 1 plus 10x. So you can define this non-convex function, and you can plot it from minus 1.5 to 4.4, for example, as you can see it here. Now we need to find x, which will minimize this function. And as you can see here, if we are starting from the right-hand side, it's strange. I have a problem in. I cannot type anything. Yes. So if you are starting from any point to the right-hand side, you will end up in one of those local minimas, for example, if you are lucky, and if you will start from the left side, maybe you will end up in this global minimum. So it's according to the starting point, in fact. So if we are lucky, we can start from left. If we are not lucky, we can start from the right, for example, from the middle. And in this case, maybe we will start in one of those local minimas. So this, I need to differentiate this function to get the gradient. So I just, in Python, I used there's something called symbols. So I define x as a symbol, for example, and I defined my function here. As you can see, fx equal this function. And then now I need to differentiate this function. So I will call it the f. It will equal fx dot differentiate with respect to x. So just to differentiate this function, because it's complex function, so it's much better to use Python for doing this for us. To substitute value to the function, to f of x, you need to use lambda lambda def y x. I mean, you need to send a value of x to the function of x to get the value of fx of x, or as a df for x, the same. So also just a way for substituting a value x to this symbolic function and get its value. And the gradient descent, it's as it has been defined last time. So we need to run this one for 100 epoch, for example. This is eta, and the momentum term, I called it beta, for example. I put it 0 value, for example. You can define the value of x as a random value from minus 1.5 to 4.4, or just 4.3 if you want to start from the right. If you want to start from the left, you can select minus 1.4. And you just use our function, our stochastic gradient descent, as we know. So we need to calculate delta x. So delta x will be eta multiplied by the first derivative, the gradient. So it will be eta multiplied by df of x plus beta multiplied by delta last delta x. So delta underscore x0, which is the last delta x. So I calculate delta x each time, and I just define the delta x0 equals 0 in the first iteration. But after that, we will update delta x0 by delta x. And after that, I will update the value of x. So x equal x minus delta x, because we calculate delta x. And in this case, delta x will be eta multiplied by the gradient plus the momentum term. You can put beta equals 0. When it's 0, it means you don't have any momentum term, for example. So it's just the approach which we did last time. If you want to increase it, you can just put it one time 0.2, 0.5, 0.6, and so on. And you have the code here if you want to look into this code. And as you can see here in this graph, for example, I will start from the right. So in this right, we are starting from right. Do you see? So we are starting from the right side, from here. In this case, I don't have any momentum term, right? So I put momentum term equals 0. So in this case, we will end up in this local minima. But in this figure here, if you add it 0.5, for example, you can see we have more momentum. In fact, do you see it tried to jump out this local minima, but it couldn't because the momentum term is still small value. So we are starting from the same place, and we have a momentum term, and this momentum term, it tried to swing. It tried to help us to just speed up the, keep the momentum and try to jump out from this local minima, but it cannot, because still the momentum term is very small. To the right side here, if we are starting from the left-hand side, we were lucky because it's by chance that this global minimum, it's located here. So we will end up in this place without any momentum term. It's just because we are lucky, in fact. Here also, if you are, we are starting also from the left-hand side. We try to go out from this local, but we don't need, in fact, to go out from it, because this is the local minimum, which we need to, but because it has too much momentum, it tried to go up, as you can see here, but it go down again because at some point we will go back again to the same point because we need to minimize, in fact. In the next slide, yes, in the next slide here, it's from the left, but I try to increase the momentum term to 0.9. So as you can see here, because we have big momentum, we jump it out from this local minima, global minima, which we want to keep, in fact. But because we have high momentum term, we went to the middle, but we went back again because we minimize, right? Because in fact, we go in this direction, in the direction which increases the value of x, as you can see here. So here it's from minus to positive. So when we are starting from the left side here, it's the direction which will increase the value of x. And when we reach this place here, the gradient equals 0, but we have the momentum term. So the momentum term, in fact, it helped us to go above because we came with high speed. As you can see here, when you are coming from the left side, you are coming with very high speed or with high momentum because the gradient was very large value here. It's very steady. So it goes out from that place, but it went back again to the same point because the gradient has different sign, in fact, and it will be negative, right? And in this case, we will go back again into the direction which will increase the value of x. So when you are coming from the left side, we move in the direction which increases the value of x, and when we're coming from the right side here, we are moving in the direction which will decreases the value of x. And at the end, we will end up in the local minimum, which is our target, right? So you can see here the impact of the momentum term. So momentum term is very useful. In fact, it's very, very useful, and there is no harm if you have a large momentum term like 0.9, for example. You will explore some other areas, but at the end also you will end up in the local global minimum. Here in the right hand side, I try to, we are coming from the right side because this right side is complex, because maybe we will stuck in this local minimum here. I increased the momentum term to 0.9, 0.8. So we jump it, we cross to this local minimum, but we stuck in another local minimum here, right? So it's not still optimum, because this one, it's not our target to be here and not our target to be in the middle here. Our target is to reach this global minimum. So we need to increase it more little bit. So when we increased it little bit, we were able, in fact, to cross this area and to end up in the global minimum, right? As you can see it here. So are coming from up with very high speed, right? And we using the global, using the momentum term, we were able to build momentum and to go faster until we are able to reach this global minimum. So momentum term is very, very useful in this case. So if you want to compare, you can just compare between this case, for example, where momentum term equal 0.9, because we're starting from the right-hand side, and this right-hand side is the more complex one, in fact. And the last slide here. You see here? So when momentum equals 0, for example, we will stuck here in this local minimum. But when we increased the momentum term to 0.9, we will be able to jump and try to reach this global minimum, which is very useful. So momentum term is very, very useful, but it will make your model more complex because you will have one more parameter which you need to adjust. But it's something which is very, very useful. Yes, I try also to, because we have this adaptive learning rate, for example. So if you want to use eta as a fixed value, so because we defined eta equal 0.01, for example, so the performance was like this, as you can see. You can see that we are moving at a fixed speed, correct? When we are not adaptive, because the step size is fixed. I mean, we have fixed step size or fixed learning rate. So as you can see here, we are moving at the same speed in the left-hand side. So we're moving at the same speed. I try to make it more adaptive, for example, because I need to travel at the beginning at high speed, and when we are reaching the local minimum, I need to lower my speed. So I use this formula, for example. So it's eta multiplied by I divided by I plus 1, which means if you are at iteration number 10, for example, you will multiply this eta by 10 divided by 11, right? 10 multiplied divided by 11. You can just say at iteration number 2, this one, it will be 1 divided by 2. So it means we, instead of using the full learning rate, it will be half value in the next iteration. And it will go down step by step until we converge. So in this case, as you can see here, we are traveling at high speed at the beginning, and we try to reduce the speed when we are reaching our local minimum, right? When you divide it by I plus 1, it will be also more, the break, it will be more tough here, in fact, as you can see here in the bottom here, in the figure in the bottom. I multiply eta by 1 divided by I plus 1. So which means at iteration number 1, we will divide by 2. At iteration number 3, for example, we will divide by 4. Iteration number 5, we will divide by 6. Iteration number 100, we will divide eta by 100 plus 1. Right? So the break here will be more stronger. So as you can see here in the bottom figure here, we are coming with very high speed at the beginning in the first iteration, and our speed goes down until we reach our global minimum, right? So in this case, we will avoid any oscillations. I mean, in this graph, in fact, if you increase the value of eta, you can see that you can oscillate, right? So if you want to test high value of eta, for example, when you increase the value of eta, maybe you will be able also to reach very quickly to this global minimum here, but you will oscillate across this place. It will, maybe you can just oscillate forever, right? Because eta value is very high. So we'll keep jumping across the local minima, the global minimum, and you will not be able to reach a point where the system will converge because eta is very high. So in fact, you have the code. You can play with the code. You can try to increase eta. It was also a good idea, in fact, to increase eta because eta value here is very small. But if you want to test different eta values, it will be also nice. So small eta value and a large eta value. Small eta value, step size will be very small. So in this case, we will take more number of iterations to reach, to converge. If you will increase eta, so in fact, in this adaptive learning rate here, it's smart to start with really large value. It was better to start with large value. So we can start at very high speed and also when reach the global minimum, it should be reasonable, not very slow. So, so the eta value, in fact, it will impact number of iterations which are required to reach this global minimum. Yes. So I did that part last time because I got feedback that we need to maybe cover that. So do you have any question for that part? Any questions?
One question, like, is there like a method? How can you, for example, know how many iterations you should go until you converge, or like, so this is just something that you can kind of come up with experiments?
I guess you need to experiment this. So usually we select a larger number of iterations to be sure that we will be able to reach this to converge, for example. Maybe in this code, for example, I just put here a condition, for example, when the gradient is below some threshold value, I can quit the for loop, as you can see it here, for example. So if the absolute value of the gradient is less than or equal 0.01, for example, just to go out, stop. So so you can put any termination conditions. You can call it termination conditions. You can keep running until for the full set for number of iterations, for example. But also maybe you can select a larger number of blocks, and at the same time you can put another condition which will make your for loop a little bit slower to check this one each time, for example. So you can calculate the absolute value of the gradient, for example, or any other. Maybe you can calculate the accuracy, for example. So when the accuracy is 95%, you can say that now it's enough, right? So also number of iteration. In fact, it's a hyperparameter also, because I mean, maybe it's based also on your time, your computational resources, the size of the data set, for example, how much time each iteration takes. Maybe in larger systems or larger models, it might take maybe 1 day, for example. So in this case, you cannot go for larger number of iterations. But also we can use a stochastic gradient descent, I mean batch gradient descent, or mini batch gradient descent, for example. So it's a way to speed up the process, for example. Okay, I will try to send you the link for. I will put the link for the video from last time in Blackboard. So any other question for this part? Any questions? Do you want to test the code? Should we run the code together, for example, if you want, or? So you have the link for the code. You can just play with it, for example, and try to. I mean, this function is very nice because it's non-convex. Yeah, I cannot hear you.
Yeah, sorry. I just wanted to mention that I think it's nice to play with this by myself. So for me, it's okay to move on. But it's nice to have the code and to play with it. Yes,
you have the link already for the code, so you can just try to. I mean, yeah. Okay. Yes, last time we talked about this adaptive linear unit, and it's exactly the same as perceptron, except that we have different. We have this linear transfer function, and we will not use perceptron learning rule here, but we will use a stochastic gradient descent, for example, and the cost function will be the sum of squared error. For example, you can use this kind of cost function, but it's exactly the same. So we will calculate also net. Net will be omega x plus b, right? And you will calculate this summation, and after that you will apply this. It's any activation function. You can use a sigmoid function, for example. If you want to fit a sigmoid function, it's 1 divided by 1 plus exponential minus net. You can multiply by e to the power of net. So you can just write it as e exponential net divided by 1 plus exponential net. And after that, you will calculate the error here, and you need to calculate sum of squared error, and you need to use maybe stochastic gradient descent to adjust weights. So we will not use perceptron learning rule, but we will use stochastic gradient descent in this case. So this model, for example, you can just combine those models together and create your feed-forward neural network. I think also I have something which I forgot to maybe to mention. It's from last time also. Yes, because this example also, we used this example last time, sorry, but I forgot to mention it. Because last time we need to use a perceptron for modeling OR and 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 XOR, for example. And in case of XOR, the data set will be complex. So you need a minimum 2 lines to divide your data set because it's non-separable, for example. In this case, we need to have 2 lines. We need to get this 2 lines to classify the XOR data set into 2 classes. So this green and red. So all points which are located between the 2 lines will be classified as it's a 0, 1, 1, 0. It will be classified as 1, and the other points, the green points, will be classified as 0. So we used a perceptron last time, and to implement a perceptron in Python, it's simple. You can just define a function called the perceptron, and it has inputs, weights, and bias, for example. And just for each time you will calculate net will be weights multiplied by x plus bias. So it's omega x plus b. And after calculating this value, this net value, you need to apply this value to the activation function. We will have this step activation function. So if net is greater than or equal 0, y will be 1. So the output equal 1, otherwise output equal 0. So this is very simple implementation of your perceptron. If you want to use it with AND, you just need to define your weights, because last time you have been working to get those weights by yourself. So for example, the weights will be 1 and 1, omega 1 equal 1, omega 2 equal 1, and the bias equal minus 3 divided by 2. And this is my data X and target. So this is my truth table, and this is my targets 0, 0, 0, 1, which means it's AND. And after that, we will find that because we need I need to plot this line, this straight line, the decision line, and the decision line, in fact, it's omega 1 x1 plus omega 2 x2 plus p equals 0. So if you can define x1 with those values, you can get x2, which will be minus omega 0 divided by omega 1, for example, multiplied by x1 minus b divided by omega 1. And you can just plot. So in this case, you will get this response. In different way, you can also define the value of x1. You can define the value. This is x1 in x-axis, x2 at y-axis. So I can define values for x1 and x2, and I can use this function, which is mesh grid. So I will generate a grid with some accuracy, right? I generate all points, all values between minus 0.01 and 1.1 to cover all points. And I will send all those values to my perceptron, right? So just send all those values to your perceptron, and the perceptron will classify it, because we have the perceptron, and we have the weights, which we defined here, and we have the bias, which is defined here for AND. And it will classify the AND data set, and at the end, we will plot my decision line like this one. So you can do it like this one, or you can do it like this one. Here, we can use this approach when it's very simple, when it's a perceptron, for example. But when it's feed-forward neural network, it will be complex to plot the decision boundary by this approach. And we need to use the perceptron itself or the feed-forward neural network itself. So in this case, we can plot the decision boundary, and it will look like this one. This is for AND. For OR, it will be the same also, but the data set will be different. So we have the data set. I mean, the data set X will be the same. The X values will be the same. The target value will be different. So it will be 0, 1, 1, 1, for example. We need to define also omega and B. Maybe it's defined in the code. Omega 1, it will be equal 1, omega 2 equal 1, and the bias equal minus 0.5. And we can do the same as well. So we can plot the decision line like this one, or we can plot a decision surface like this one. So all data points which are located above the line will be classified into ones, and all data points below the line will be classified into zeros. In case of XOR, this is very complex because one perceptron, we can get one perceptron for each decision line. But in case of this data set, we need to generate 2 decision lines. So in this case, I need to get one perceptron to get this line, and I need to get another perceptron for generating the below line, this line. And at the end also, I need to have a perceptron to combine the 2 lines together so we can combine the decision, right? So the result will be a simple feed-forward neural network, which consists of 2 layers. The first layer will consist of 2 perceptrons or units or neurons, and the output layer will consist of 1. So this one will be very, very simple feed-forward neural network. It will look like this one. So last time for AND, for example, we used this perceptron alone. So the input was x1 and x2, weights was 1, 1, and the bias was -3 divided by 2. So this is the AND. For the OR, it will be the same. The input will be x1 and x2. The weights will be the same 1, 1, and the bias will be -1 divided by 2, -0.5. So the top one, it will be AND. The bottom one, it will be OR. And at the end, we need to subtract. If you want to get XOR, as you can see it here from this truth table, XOR, it will be OR minus AND, right? So it will be OR minus AND. So the weight here will be 1, and the weight here will be -1, which means this output perceptron, it will combine the 2 decisions into 1. So we'll just subtract OR minus AND. So you can see the meaning of weights here. So it will be the output from OR minus the output from AND. And of course, we select the bias because we need to make decisions, because we need to define a line. So this line will decide, which one above, which one below to make a decision. So at the end, we have the XOR will be like this one. So we have 2 weights here, one for AND and one for OR. So we need to define omega1, B1, omega2, B2, as we did before. We need to have our own data set. So we have those input features, x1 and x2. We have the target features. It will be 0, 1, 1, and 0 for the XOR. In this case, I will just call it feed-forward neural network because I cannot call it a perceptron. So I will define my feed-forward neural network, FNN. We will send X and we will get targets or predictions. So this is the targets, 0, 1, 1, 0, and those are the predictions, 0, 1, 1, 0, which means we are able to build our first feed-forward neural network in this way. So this is a function of feed-forward neural network. So we will apply omega1 and the B1, and we have those weights omega1, B1, omega2, B2. So we will do it for H, for example, right? So it will be hard limb. I defined this function, which is a step function or hard limb function. So the first one will be hard limb omega X plus B1, right? So this is the first output, or the output from the first perceptron. The second perceptron will be omega2 multiplied by, this is the first layer. So the first layer will be omega1 multiplied by X plus, I guess there is something missing here. I don't know. Because omega, yes, this is the width. In fact, this is the width for the hidden layer. So the width for the hidden layer will be 1, 1, 1, 1. It's I just combined it into one matrix. So 1, 1, 1, 1. So it's for the full hidden layer. The bias will be -3 divided by 2 and -1 divided by 2. And for the output layer, it will be -1, 1, and the bias will be -1 divided by 2. So the output from the hidden layer, it will be like this one. It's the same as the same equation which we used for the perceptron, but instead of using vector multiplications, it will be matrix multiplied by vector. So omega1 will be matrix. It will be 2 times 2 multiplied by the input, which is X, which is a vector, plus B1, which is a vector. After doing this, we will get H. And H here, it will be vector, right? If you can multiply it here, omega1, 2 times 2 multiplied by X, which is 2 times 1. So 2 times 2 multiplied 2 times 1, it will be 2 times 1. So it will be vector plus vector. So the output here will be a vector. For the output layer, it will be omega2, which is this vector -1 and 1. It's a column vector or row vector multiplied by H, which is the output from the hidden layer, plus B2, which is a scalar, -1 divided by 2, so you will get 1. So it's very, very simple, and it's feed-forward neural network, right? But we don't train the neural network here because we defined omega-1 B1, omega-2 B2 manually, right? If you want to plot it, it's the same. We need to define x1, we need to define x2. We can use this mesh grid to generate a grid, so we can have a nice graph. So I get x grid, y grid from this function, and I will send those values to my feed-forward neural network, and I will get predictions. And once you have your predictions, you can use a scatter plot, for example, to plot xg and yg, for example. And in this case, it will look like this one. So this line is OR. This is a decision line which we got from the perceptron, which classify OR, and this line which is AND, in fact. And at the end, we will get OR minus AND, because that part is AND. So we need to subtract. When we subtract OR from AND, we will get this yellow area here, which is the XOR. We did that last time, and I also said, okay, maybe it's nice also to try to polish it and put it more clearly in the slides. So you have also at the same, you have this perceptron logic. You have link for the code. You can open the code and try to play with it if you want. Yes. Do you have any question for this OR, AND, and XOR? Or it's simple, too simple? Yes. So this is adaptive linear unit. We did that last time already. So it's also to just revise quickly. You need to define the cost function. So the cost function will be sum of squared error. It will be this equation. And this is the way how we update weights. So omega equal omega, or omega k plus 1, or equal omega k plus delta omega k. Delta omega, it will be minus eta multiplied by the gradient. So the gradient, it will be the first derivative of j with respect to omega, right? So partial j by partial omega, it will be, we will use chain rule. So partial j by partial omega, it will be partial j by partial y multiplied by partial y by partial omega. Partial j by partial y, it will be 2 times half multiplied by t minus y multiplied by the first derivative of minus y, which is negative 1. So it will be that part. And the partial y by partial omega, y equal, you can see here, y equal net, correct? And the net equal omega x plus b. So partial y by partial omega, it will be x. So at the end, it will be delta omega, it will be minus eta multiplied by this partial g by partial omega. We got new negative here, multiplied by x. So at the end, it will be that part. So it will be eta multiplied by error multiplied by input, right? So delta omega, it will be eta learning rate multiplied by the error, or sum of error, for example, but it's just error, right? Multiplied by x by the input. So if I want to update omega 1, it will be eta multiplied by the error multiplied by x1. If I want to update omega 2, so I need to calculate delta omega 2. So delta omega 2, it will be eta learning rate multiplied by error multiplied by x2, right? If I need to update omega n, so I need to calculate delta omega n. So delta omega n will be eta multiplied by error multiplied by xn. So if you want to, you can import it, in fact, from sklearn if you want, but also it will be nice if you can do it by hand. So try to do it by hand, right? But here in this example here, because it's called the logistic regression model. So this logistic regression, you can import it from sklearn.linear model. It's linear model, and it's called the logistic regression in sklearn. So you can just import it and use it. And you need to send x value and y value, right? Because we need to fit those y value. So you have x and y, you have the input features and target feature. You will do this, fit the model with the data, and after fitting the model with the data, you need to print your coefficients. So we need to get omega 1 and omega 2, for example, those coefficients, and intercept. Intercept is the bias. So the coefficient and intercept, those are the model parameters. And this logistic regression, it's fitting this linear model here, right? So don't have this unit step. If you want to use it for classification, because this linear regression, logistic regression, people usually use it for regression problems. But if you want to use it for classification problems, you need to add the sign part. You need to add step function. So the step function, in fact, it's hard lim or sign, right? This function here, if you want to add. It's a sigmoid, sorry, I just added sigmoid, but I don't know why I put this one here. In fact, maybe we will need to have this one here. So, so the net will be omega multiplied by x plus b. If you want to plot the decision line, you need to find the net. So net here, it will be this bias plus omega multiplied by x.
Sorry.
Yes.
This is just like perceptron, but the activation function instead of linear function, we use like a logic function, and then we add something to, like, because the output is like a real number, so we add like something that turns it into like a integer, kind of like a 0 and 1 at the end.
Yes. For example, because this one usually they use it for regression problems. It's a logistic regression classifier. So you can use it for regression problems, but if you want to convert a regression problem into classification problem, you need to convert the output into 0 and 1, for example, using step function. Or if you want to convert it into +1 and -1, you need to use also the other function. Do you remember? So this hard lim, it's a symmetric hard lim function, right? So it's a step function or symmetric step function, which we used last time. If you can go back to it very quickly. Yes, so maybe not this one, I don't remember. We had it last time. Yeah, maybe I was moving and I'm not, okay. This function, do you see? You can use this step function or sign function, for example. They call it sign function or symmetric step function. So if the output, if your target feature is a number between 0 and 1, for example, I can use this function, step function. If your target values are +1 and -1, we can use this one, right?
And one thing, like when you use like a sigmoid activation function, our perceptron kind of model can classify like X or kind of, I don't know, non-linear functions. Yes?
No, it's this sigmoid function. It will give you the probability that this example belongs to this class. Okay. So, for example, you can put a threshold. So, I mean, in this adaptive linear unit, for example, you can decide by yourself as a threshold value. So you can say that all values which are greater than 0, it will be converted into, look. So all net, one net is greater than 0.5, it will be 1. Otherwise, it will be 0. So you can use this function to convert the output into classes. But if you want to use sigmoid, in this case, it will be like probability that this example belongs to this class, because it will be number between 0 and 1, right? So if it's 0.8, you can say that, okay, this is a probability that this example belongs to this class, for example. So the selection of the activation function, or I mean, it's based on your data set, right? So we need to select something which is matching my data set. Or you can try to modify your data set to match your model. So it's either ways. Is it fine? So in a perceptron, we update weights after each individual training sample. And in this case, it will be stochastic gradient descent. But sorry, in perceptron, we use perceptron learning rule. In case of adaptive linear unit, you can still calculate the gradient and update the weights after each individual training sample, which is SGD, stochastic gradient descent. But also you can calculate the gradient and update the weights based on the whole training data set, which is batch gradient. So in case of batch gradient, we can calculate this average mean gradient, for example, for the whole data set, and update my weights only one time each epoch. So if you want to update each iteration, we will call it stochastic gradient descent. But if you want to update one time each epoch, for example, so in this case we can call it batch gradient descent, right? So I have number of epochs. I will train my model for a number of epochs, but in each epoch I can train my model, update the weights one time each for each example. So in this case we will call it SGD. but you can calculate the average gradient, for example, for the whole data set, and update your weights only one time each epoch. So in this case, the learning rate maybe will look like more stable or more robust. So we can talk about those training mode. We have this stochastic gradient descent, which is called also online training. So we train the model example by example. So we apply one example and we calculate the error, and we calculate the gradient, for example, and after that we update the weights each example for each example, and therefore they call it online learning. So if you have a model, for example, which is implemented in IoT device, and you are collecting data from time to time, each 1 hour or each 30 minutes, for example. So once you have a new example, you can update your weights. You don't need to keep your data or store your data for a period of time and update your weights. You can do it, for example, you can maybe keep 10 data points each time, and when it's 10, for example, you can just do one epoch, for example, or one training, for example. And in this case, it will be called batch gradient. So in batch gradient, we calculate the gradient based on the whole data set. In mini batch gradient, we divide the data into mini batches due to many memory restrictions. So if you are working with videos, for example, or YouTube videos maybe, and it takes space in the memory, and your GPU memory is not big enough. So in this case, you can just use mini batch gradient. So in this case, instead of using the whole data set for calculating the gradient for the whole data set and updating your weights, you can just divide your data sets into small batches, so it can your memory can accommodate the size of this mini batch. Large learning rate may be overshoot the global minimum and they fail to converge or even diverge. It would be nice if you can go to the example which we did today, for example, and try to increase the learning rate and decrease the learning rate and try to see the impact. So when you increase the learning rate, you will overshoot. You will overshoot the global minimum, and it might fail to converge, or it might diverge, in fact, right? Because the sign of the gradient will be, sometimes it will be positive, negative, because we are oscillating or overshooting. So sometimes it will be positive and negative. So it might, you may stay forever, just oscillating across this global minimum. And then maybe also you can diverge. So please go back to the code which we did today, which we tested today, and try to increase the learning rate and try to see the impact on the performance of your gradient descent. So I don't know what this implementation, it's adaptive linear unit. If you want to implement adaptive linear unit, this is an example. I try to apply this adaptive linear unit to iris datasets. So it's the same. Also, we will use the first 100 points because the first 100 points are for two classes. So it's iris setosa. First 50 it's for iris setosa, and the next 50 for iris versicolor. So in this case, we will use the first two blocks because I need to convert my problem, because it's a perceptron, and we use perceptrons for binary classification problems. So I need to convert my problem into binary classification problems. So in this case, we will select the first 100 points, which are, related to the two classes. So I will select the 100 data points, and I will select input features, feature number 0 and feature number 2. I don't remember the name. Maybe it's iris, it's petal length and petal width, I guess. Petal and sepal, I guess petal length and the sepal length, petal length and sepal length, maybe. So we'll use two features. I just use the two features because we need to plot it in two-dimensional space, but it will be also nice exercise if you can work with 3, for example. So in this case, you need to plot, the decision line in three-dimensional space. So, so the target feature, as you can see here, I adjusted the target features. It's also the first 100 points. So the target feature, it will be the first 100 points. But in fact, I converted it into 1 and the -1. So it will be 1 for iris setosa and the -1 for versicolor. So in this case, I cannot use a step function, and I need to use sine function, right? Okay. Okay, so this is the function. We wrote the code from scratch. So you need to initialize, I mean, your adaptive linear unit, for example. I just define number of epochs, and by default it will be 100, and the learning rate it will be 0.1. It will be nice, also good exercise here if you can add the momentum term, for example. I mean, we added the momentum term before. It will be nice if you can add the momentum term here. So the input of the function will be the training inputs and the training labels. So x equal training inputs, t equal training labels. I need to have a function where we can store the cost functions or the error function over each epoch, for example. And we will initialize the weights by random. So number of weights, it will be number of training, the size, the dimension of that number of column plus 1, because we have omega plus p, right? Yes, someone, any question, please?
Right, you were mentioning about momentum term.
Yes.
Could you just remind it?
Do you need to have it here?
Yes,
You
if
just-
it's going to be later, yeah.
Yeah, it's not here. It's this example. I just did it for just training for eta. But if you want learning rate, I have only here training rate. But if you want to add momentum term, it would be nice. I mean, it would be nice exercise if you can add momentum term here in this function, right?
Mm-hmm.
So how
Yeah.
can you add it?
Yeah, my question was what is momentum term?
You just came. You didn't attend with us from the beginning.
Well, I read it before. No, I have some experience, but I just cannot very quickly to implement that. So.
But you are not attend. You didn't attend with us from the beginning, right?
Yes, that's my second class. Yeah.
No, from today, because today we talk about this slide.
Yeah.
This
yeah.
is a momentum term. So I mean, this is the training rule, for example, omega equal omega plus delta omega.
Yeah.
So delta omega equal minus learning rate multiplied by the gradient. So we will add here this momentum term here. So it will be a factor or coefficient multiplied by the last delta omega. Right? So this is the momentum term, and it helps us to to accelerate the gradient, so we can converge faster. So this is the momentum term.
Okay, thank you so much.
So in the example, we just use the learning rate, but in this time here, we added momentum term multiplied by the last delta omega. So we have those examples. If you didn't join us, I mean, we used this non-convex function. So we have some local minimum and the global minimum. We need to reach the local minimum. If you didn't use momentum term, and if you are starting from the extreme right-hand side here, you will end up here, in fact, in one of those local minima. But if you are lucky, because we are selecting omega in random in each, when we train the model, we select omega by random. So we don't know from where we will start. If you are lucky, you can start from the extreme left side here, right? And from the left-hand side here, we will end up in the global minimum, which will be okay. But there is no guarantee. So in this case, we need to use momentum term. We implemented this momentum term here, as you can see. So delta x equal eta multiplied by the gradient plus beta multiplied by last delta x. And this is the updating rule, x equal x minus delta x. And the delta x is 0 equal just delta x. So just you need to make those small changes to the code so we can add this momentum term. And here we just explained it for last time. We are starting here without any momentum term from the left side, and we ended up in this local minima. And in the right-hand side also, because we are lucky, we started from the left-hand side. We ended in the global minimum, but it's by chance. There's no guarantee, in fact, that our cost function will be similar. Here we try to increase the momentum term. When we increase the momentum term, we increase it to 0.5. But it's still not enough to push you out from this local minimum, right? If you are at the global minimum, it's fine because there is no harm, in fact, of having this momentum term. So there is no problem because you will end up in this global minimum, hopefully. Yes. Any question?
Ibrahim, can you just compare the code and the equation for the momentum? I think there is inconsistency.
In the code?
code and the equation for the momentum. I think the sign is mistaken or something. If you go back 2 slides, then you will see.
Yes. Look, we calculate delta x, right?
So here you have x minus delta x. That means it's minus eta minus beta. And when you go to the equation, I think you stated minus eta plus beta.
Yes, yes, I can fix it. Yes, this one.
Yeah. Here the other equation.
But
I
this
think
one
should be minus momentum times.
Yes, this is correct, because it should help us. In fact, we should move in the same direction. So if it's positive, it will be a problem. Maybe we need to put here. Maybe I will fix it. Yes. So in this case, this momentum term, it will help us. I mean, this slide, maybe it's a nice one, because here we can see that using this momentum term, it can push up out of this local minima here, and we can, but maybe it was not big enough, because in fact the momentum term here was very high, but here it's not big enough. I mean, it helped us to go out from this local minima, but we stuck in another local minima. But the reason for this, because the gradient here is smaller, right? So the momentum here will be much less. So for the same example here, you can just say that why you are going out from this. Yes. And we stuck here in the middle here. We stuck here in the middle because the gradient here is much less than the gradient here, because it was very steady here, right? But if we increase it from 0.8 to 0.9, it will help us. It will be big enough here in the middle to just try to go directly into this global minimum. And for the left-hand side here, because this is the global minimum, right? So, I mean, it helped us. I mean, it pushed us out from this global minimum, but we will be able to converge again and go back again to the global minimum, which is very good. So this is the idea of having this momentum term. So I hope that it's, I mean, in this example, what is missing here, in fact, just to try to test different values of eta. Try to, I mean, here in this example, I'm using very small value of eta. It's 0.1, I guess. So try to use 0.2, 0.5, for example, and I try to see what will be the impact on the system conversion, because it might oscillate at some point. So we need to increase the value of eta until it oscillates. So we can just see how it will oscillate and the impact of eta on the time required for the system to converge. Yes. So we will go back again to this example. This example, it's just we calculate net. It will equal omega x multiplied by b, omega x multiplied by b, y equal net, because we use linear activation function. So here we don't have anything, it's y equal net. So it's a linear activation function. We calculate the error, which is t minus y. And after that, we will update the weights. So delta omega equal eta multiplied by the error, multiplied by the x, by input x, right? If you will take the mean value here, it means we are using a batch gradient, right? So here it's eta multiplied by error multiplied by x, and we take the mean value, which means we are using batch gradient. We do it for omega, we do it for beta, for bias. So for the bias, it will be eta multiplied by the error. We don't have negative sign here, right? Because if you look into the equation here back again, I mean, this is the equation, right? We have negative multiplied by negative. I mean, delta omega, anyway, it's minus eta multiplied by the gradient. But the first derivative by partial g by partial y, we got a new negative sign here. So negative multiplied by negative, it will be plus. Yes. So we will do this, and at the end, I want to calculate the cost value or the error, for example. So it will be the same equation, half multiplied by squared error. And of course, you need to take the summation over maybe this. I mean, for those the whole data set, because I apply here in each epoch I apply the whole data set. So I need to take the summation or to take the mean. It's a sum of squared error. I mean, this equation, it's a sum of squared error. So it's 0.5 multiplied by summation of squared error, and therefore I'm writing it like this one. And I will keep it for plotting. So this function for training, and I need to have another function for prediction, for example. In case of prediction, I need to send the inputs and get maybe the predictions, correct? So it will be omega multiplied by x by inputs plus bias. And I need to return, here I just made it very compact. So I calculated net, and I will return 0. I will return 1 when net is greater than or equal 0. Otherwise, it will be -1. So I'm just using the sign function here in a very compact way. As you can see, it's here. And this is the response. So we are starting with very large error. And in each epoch, we try to reduce this error until it's close to 0, for example. So it will be very, very nice here. I'm using here very small eta value. It will be nice here if you can try to use, for example, try to use add momentum term here in this learning rule. So at the end, I need to plot the performance of my system, and I want to plot the decision boundary. So I will plot my data set using a scatter plot, and I will to get this decision line here. So we know that this decision line, it's omega 1 x1 plus omega 2 x2 plus b. If you have x1, I just need to get x2. So I assume the values for x1, right? And after that, I will find the equation of x2, which will be the weights, omega 1 divided by omega, this one x2. So it should be omega 1 divided by omega 2 multiplied by x1 minus 1 divided by omega 2 multiplied by bias. So this is the decision line, equation of the decision line. So if you can assume values for x1, you will get values for x2, and you can plot it. So you will get the decision line like this one. So in this case, as you can see, for this iris data set, I used this adaptive linear model, for example, and it can be used for classifying this iris data set successfully. Usually it is used for regression, but because we use this sign function here, we can use it for classification. So in fact, any regression problem can be converted into classification problem. So just you can try different learning rates. For example, I just increased the learning rate a little bit, and when you increase the learning rate, you will diverge. As you can see here, it's here. I mean, it was anyway very, very small value, but when you increase a little bit, your system will diverge. You will not be able to converge. So how to improve the gradient descent is through feature scaling. We have been talking last time about those feature scaling, for example. One way is to use a standardization, which will shift the mean and variance of each feature so that it is centralized at 0 and has a feature standard deviation of 1. So it will be normally distributed. So it's simple. It's just for each column of my features, I need to calculate the mean value and the standard deviation, and I need to subtract each x from the mean value and divide it by standard deviation. So it will be x minus mu divided by sigma. So if you need to normalize or standardized, if you need to standardize, it will be like this one. It will be x minus x mean divided by x dot standard. So it should help you to get better performance. So when we I'm getting so it's just I retrained the model again using x normalized, for example, or standardized, for example, and the performance also will be like this one. So yes. Do you want to take a break or something?
Yeah, short break is always good.
Okay. Yes. Okay. Thank you very much. We can take 10 minutes break because, in fact, I have I need to go to the hospital because I have an appointment. But we can just take 10 minutes break. I would, and we can discuss after 10 minutes if we will continue or if we can close today.
So do you need to stop earlier today?
Yes, in fact, because I got something at night and I need to go to the hospital to check it.
No, sure. So when should we stop?
It's 10:30. In fact, because the hospital is far from here,
Okay.
it takes maybe
Okay.
30 minutes. So,
So-
but we can talk after 5 minutes. I will just make some calls and to check my appointment, and we can talk again after maybe 5 minutes or 10 minutes.
Okay.
So we
Okay.
can just take a break, and after 10 minutes we will discuss.
Okay.
So, thank you.